Okay, so we'll be looking at chemical process calculations with a second year first semester course, and then it's very needed in chemical engineering. Um, with the course content for today, we'll try and then look at the introduction to the course. We'll also talk about unit processes and unit operations, and then we'll also talk about some calculations when it comes to chemical engineering. And if possible, we can start a little bit of the material balance today. So with this one, when you talk about engineering, is you applying scientific knowledge to solve societal problems. Right. So that's the whole idea about engineering. So when you say we are engineers, you actually want to solve a problem using scientific knowledge. And then these are the engineering methods we go through before you can actually solve a problem. You first have to identify the problem, you have a team, because as engineers, you can't work alone. You definitely need a team. And you also identify constraints, you set for solutions. Of course, you can get more than one solution, but then you have to analyze each of them and then you select the best solution. And like Doc said yesterday, we have design, then we have the construction. Right. So the design is like the paperwork, and then the construction is you actually bringing the thing into the system or bringing into reality. Sort of like building the thing itself. Doc also spoke about chemical engineering yesterday, so I think I can skip this ones too. And then with the unit operations too, he also spoke about unit operations and the unit process. So the unit operations just involve a physical means, right? But then with the unit process, like there's always a chemical change in the composition. So now when you compare these two, unit operations here and the unit processes. So the unit operations, you realize that it's always about a physical process, like fluid flow, heat transfer, something that we can relate physically, as compared to the unit processes, which involves like changing the chemical composition. So in the unit processes, it involves a chemical reaction. So when it takes something like oxidation, you're actually adding oxygen to a compound, and that actually changes the chemical composition of that new product formed. Right. But in the unit operations, just physical processes, either a separation process or something. Now, so we're actually starting with this unit and then dimension. When you talk about a dimension, it's just a property that can be measured. Length, mass, time, or anything that we can actually measure. It's called a dimension. And then the unit is what is used to characterize the dimension. So let's say when you talk about length, which is a dimension, each unit becomes either centimeters, meters, or feet, something. Now, with this part also talks about you giving a dimension or giving a quantity without a unit, it becomes meaningless for we chemical engineers or even as engineering as a whole. Because when you just say the length is 2, how do you know whether it is in meters, centimeters, feet, or something? Like, so you can't just give answers straight away like that. You need to add unit to it. You have to take note of this. And then when it comes to addition and subtraction of units, the unit should be the same before you can either add or subtract. So with this example, we have 3 centimeters minus 1 centimeter. Right? If this was to be in meters and this was to be in centimeters, this subtraction wouldn't have been possible, right? Directly, unless you convert one into the other. So example of such is this question here: 3 centimeters minus 1 millimeter, which is not possible unless we convert it into the same unit before we can subtract. And now when it comes to multiplication of units or dimensions, that one, regardless of either the units are the same or not, we can actually measure them. Of course, even multiply units, different units to get a derived unit. I think you should know much about them. And then you guys also did it in um physics. Yes, I think the beginning of physics you talk about units and dimensions. We also have dimensionless quantities. So when you have a mass over mass, so such like 6 grams over 2 grams, the grams and the grams cancel out. You are left with 3. This 3 here has no units. In such case, we see this quantity is a dimensionless quantity. The reason why we are saying it's a dimensionless quantity is because it's actually a quantity sometimes. So you have something like mole fraction and mass fraction. They're actually quantities, but then they are dimensionless. And you also we have the base unit, which is they are about 7, which I recall we did it in physics too. So the mass, length, time, temperature, electrical current, light intensity. It's like a subdivision of the actual unit. So when we take let's say mass, which is kilograms, we can have subdivisions of that kilograms, milligrams, the per unit. And then we also have the derived unit, a unit for area, and area is also a quantity. But then this unit is not a base unit. It's also or dividing base unit. You get derived unit. So these are some examples of quantities and then their units. And also the derived unit also. We have systems of bringing up all these units. We have the SI system, which I know you guys have heard of it before.
Are dimensionless quantities, do they have meaning? Or do dimensionless
Yes,
quantities have meaning?
yes. Some of them have meanings. So let's say when you see I mentioned mole fraction and mass fraction. When you talk about mole fraction, it doesn't have any units, but then it actually has a meaning. I don't know. Please, that's you guys, do you get it?
Yeah, Francis.
And also,
Yeah.
if I'm to add, sometimes when you say dimensionless, we could have given them a dimension, just like more fashion, we could have called them kg per kg. But if you think of it very well, kg per kg is nothing. That's why we say dimensionless. Is that okay? It doesn't mean that they didn't really have units. It kind of had units, just that the units kind of cancel out. So there's kg at the top and kg at the bottom. So kg of, let's say, a small part divided by kg of the 2000. So it does have a unit. It's just that the units eventually cancel out. Francis can continue.
Okay. Thanks a lot. So these are examples of the derived units: volume, force, energy, pressure, density, and all that. Realize that you sometimes you need to multiply, even all the time, you need to multiply some of the base units to get the derived unit here. So these are the derived units, and then these are the base units. And then talking about the systems, I said you have the SI unit system, which is very common. So with that one, the mass is always measured in kilogram, and then the length is in meters, time is in seconds, and then the temperature is in Kelvin. And then you have the American engineering system. So with that one, the mass is measured in pound mass, IBM. Right? And then the length, they measure this in foot or feet, and the times in seconds. Even though the quantities are the same, like they're all measuring mass, but then the unit differs. And then we also have the CGS, which is just centimeter gram second. So with that one, the mass is measured in grams, the length in centimeters, the time in seconds, and then the temperature is in Kelvin. And we also have the FPS, which is foot pound second. Right? So even right from their abbreviations, you can actually get the actual unit for their quantities. And we also have the British one. So with the British, they measure their masses in slag and then their length in foot. Now with the unit conversion, we realize that from this slide, we saw that some measure their masses in kilogram, others measure theirs in pounds and slag. But when we are working, we need to communicate as engineers. So sometimes you want to convert all the units as a single one that we can all relate to. That's what you call the unit conversion. So we try to convert, let's say, a kilogram here into pound mass. Right? So I can actually relate. So in the unit conversion, we need conversion factors. And what are that factors? That factors actually show the relationship between one unit to the other. So when I take 1 meter, 1 meter is actually 3.28 feet. And that can help me convert if I have 20 meters. I can easily convert that 20 meters into feet. So that anyone who uses feet as a means of conversion or as a means of measuring length can actually understand what I'm talking about. And so these are some of the conversion factors. I think these are the basic ones you should know, like from inch to centimeters, kilogram to pounds. I think the hours to seconds is very easy. And I also have some temperature conversion factors here too. So converting from Celsius to degree Fahrenheit, this is the conversion. And also from degree Fahrenheit to degree Rankine, and then from Celsius to Kelvin. Yeah. So we have a simple question here. We are supposed to convert 30 milligram per second to kilogram per hour. 30 milligram per second to kilogram per hour. And also convert 30 pound mass per second to kilogram per minute. Yes, so with the solution, we first have our 30 milligram per second, and then we want to convert it into kilogram per hour. So we first need a conversion factor. 1 gram is equivalent to 1000 milligram. The milli, so you realize that this milligram here cancels this milligram. So you actually left it 30 gram per. So this milligram cancels this. This gram cancels this. You just have to position them in a way that the unit that you want stays and the ones you want to eliminate cancel out. Please, are you fine with that? So if here we want to eliminate the gram, then the gram should be a denominator here. So just 1 kilogram is giving us 1000 grams, so that the grams and the grams kilogram per hour. So we go ahead and try to eliminate the second. Now for this, the second is a denominator here, so we need it as a numerator here. That's why I brought the hour down. So 1 hour gives us 3,600 seconds, so that the second can cancel the second here. And then we finally get this as our final answer. So I want us to try converting like powers to. So let's say we have 400 inch cube per day, and then want to convert to, let's say, feet cube per second. You don't need to have what 1 inch cube is equivalent to in a feet cube. You just need the conversion factor. So 1 inch is equivalent to 2.54 centimeter, and then just have to cube both sides. Just have to cube both sides. I forgot, I think I didn't cube this part, but then just have to cube both sides. So when you cube this, you're actually going to cube that 2.54 here. Please, are you following? Because they are multiplying. So when you cube them, it's like 2.54 cube centimeter cube. And here also you have 1 cube inch cube, which will still be the same as 1 and then inch cube. So that the inch cube and the inch cube here can cancel out. And then you are left with centimeter cube per day. Now I also want to convert the day into hour. Right? So 1 day gives us 24 hours. Because here we want to eliminate the day, and the day is a denominator here. Right? So 1 day gives us 24 hours, so that this day and then this day can cancel out. So you are left with centimeter cube per hour. Now, if you want to convert the hour to minutes too, then because the hour is a denominator here, it's supposed to be a numerator here. So 1 hour gives us 60 minutes, and then the hour and hour can cancel out. So you are left with centimeter cube per minute. And then that becomes our final answer. Convert 5 feet cube to meter cube. And these are the answers. So when you try them, you compare your answers and see. We'll also be looking at force and weight. Now we know the difference between force and then weight, right? But then there's also a conversion factor here. When you talk about 1 Newton, we know Newton is a derived unit, and then it's based on certain base units. And these base units are kilogram meter per second squared. We also have another form of unit for a force or a weight, and that unit is dyne. This is the British form, because the British they use dyne in terms as a unit for weight and then force. And then with that dyne, we get 1 gram centimeter per second squared. But when it comes to the American engineering system, which is the AES, they use the pound force. Note, we have pound force and we have pound mass. The difference is that there is a subscript F attached to the pound here, the IB here. And then in this one, there is subscript m. Now with the pound force, when I'm converting the pound force, breaking it down to its base unit, it's not directly equal to 1 pound mass feet per second squared. As the Newton and then the dyne are equivalent to just one of them. Please, do you get it? So the whole idea is if you have 1 kilogram here, because a Newton is kilogram meter per second squared. If I convert this kilogram to pound mass, convert this meter here to feet, I'm going to get 32.174 pound mass feet per second squared. And this whole thing is called a pound force. So you can try out this example. We need to find the force in Newton required to accelerate a mass of 4 kilogram at a rate of 9 meter per second squared. We know the unit of force to be kilogram meter per second. With this one, you don't really need any conversion. You just have to multiply them. When I multiply 4 by the 9, I get 36 kilogram meter per second squared. And that's equivalent to 1 Newton. But then for this, the force in pound force required to accelerate a mass of 4 pound mass at 5 feet per second squared. Now when I multiply per second squared, and that's not equivalent to pound force, because 1 pound force is 32.174 pound mass feet per second squared. Your conversion factor here. When I multiply this, I'm getting force is 32.174 pound mass feet per second squared. The per second squared can actually come top here, so that second squared will cancel this. Pound mass cancels this pound mass, and then if so I go to this point, I was saying that when you want to find the pound force required to accelerate a mass of 4 pound mass at a rate of 9 feet per second squared. Now when I multiply these two, even though we know weight of force is mass times acceleration, when I multiply these two, I get 36 pound mass feet per second squared. But then that is not equivalent to 1 pound force, because 1 pound force is 32.174 pound mass feet per second squared. So you need a conversion factor before you can get it in the pound force that we want. 1 pound force is equivalent to 32.174 pound mass feet per second squared. The per second squared here can actually come top here, and then to eliminate this second squared. And then the pound mass will eliminate this pound mass. And then our feet can also eliminate this feet. And then we end up getting our unit as pound force. Right? And that will give us 1.12 pound force. That's all about the force and then the weight. And
Can you please take the middle one again? The force
yes,
in pounds force.
okay. We need to find the force in pound force, not in Newton. Right? And then we've been given pound mass and then feet per second squared. Now when I multiply these two, I'll get 36 pound mass feet per second squared. But then 1 pound force is 32.174 pound mass feet per second squared. So like if 1 pound force is giving me this, then what will a 36 pound mass feet per second squared give me in terms of pound force? You can use that as a conversion factor here. So you are multiplying this with this, and then we want to eliminate all the terms in order to get the pound force standing alone. And the 1 pound force is 32.174 pound mass feet per second. 32.174 pound mass feet per second squared. And I was saying that the per second squared here can actually come top here. So we have second squared here, which can eliminate this second here. And then the pound mass here will also divide this pound mass. And then the feet here will also divide this feet. So you are left with 36 pound force divided by 32.174. And that will give us 1.12 pound force. Or better still, we can do it this way. If 32.174 pound mass feet per second squared is giving you or is equivalent to 1 pound force, then what will a 36 pound mass feet per second squared give you? That will be more. Then you can do it more, let's divide. Yeah, so we know weight is mass times gravity. And then we know gravity to be 9.8066 meter per second squared. We can convert the meter into centimeters, and that will give us 980.66 centimeter per second squared. Now when you try to convert this into feet per second squared, we get this 32.174 feet per second squared. So gravity in terms of feet per second squared isn't 9.8 feet per second squared, but then it's 32.174 feet per second squared. So there's a question here that you guys can try. Water has a density of 62.4 pound mass per feet cube. How much does 2 feet cube of water weigh at sea level and 45-degree latitude and in a Denver, Colorado, where the altitude is 5374 feet and the gravitational acceleration is this? Now at the sea level, the gravitational acceleration is what is given here as the 32.174. But then that's for the first part at the sea level. Then the second part, in this condition, or this at this condition, the gravitational acceleration is this. It's like you want to find the weight, or let's say the mass. Right? So you want to find the weight, but then we need the mass first. So we can just get the mass and then multiply by the acceleration to get the weight. And we have density and then we have volume. We know the relation, right? So we can just first find the mass of water by multiplying the density by the volume. And then that will give you 124.8 pound mass. So that's the mass. Now when we want to find the weight at the sea level, weight is mass times gravity, right? And then because you are dealing with this pound mass feet second square stuff, the gravitational acceleration is 32.174, and this is feet per second squared. So you need to do your unit conversion. How do you get rid of all these to get to pound force? So our
Yes.
mass m, which is this, multiplied by our gravity will give us our weight. And our gravity here is what we are calling as G. Right? And G in terms of the feet per second squared is 32.174. So 124.8 times 32.174. When you multiply these two, that will give us pound mass feet per second squared. But then we need the weight in pound force. So it just has back to this, something like this. So now we have our acceleration to be 32.174 feet per second squared. And then we have our mass to be 124.8 pound mass. When I multiply the two, I will get pound mass feet per second squared. But then to get it in pound force, I need to do the unit conversion again. 1 pound force is 32.174 pound mass feet per second squared. Now, because the gravity is also 32.174 feet per second squared, it will cancel this 32.174. And then the pound mass will cancel this pound mass here. The feet cancels this feet. And this per second squared here will also cancel this. And then we are left with pound force. So we end up getting our weight being equal to our mass. Just because our gravity is also 32.174 feet per second squared. So when you multiply and then you convert it into a pound force, everything cancels out. Now, in
Yeah.
the Denver
Yeah.
condition, where our gravity is 32.139, so with that one, that will also be 124.8 times 32.139 before multiplied by 1 over 32.174. And when you do that calculation, you get 124.7, which is very slight. There's a very slight change. The flow rate of water through a pipe is reported as 15 cubic feet per minute. Taking the density of water as 1 gram per centimeter cube, calculate the mass flow rate in kilogram per second. You've been given the flow rate of water through a pipe, and this is feet cube per minute, which is a volumetric flow rate. But the density of water here is gram per centimeter cube. You realize that the units are not consistent because this is using feet cube, but then the density here is centimeter cube. So we need to do unit conversion here before you can even calculate our mass flow rate. The flow rate of water is 15 feet cube per minute and you have the density to be 1 gram per centimeter cube. You need to calculate the mass flow rate in kilogram per second. First of all, density is mass flow rate divided by volumetric flow rate. Forget about the flow rate. We know density is mass over volume. So if both have flow, we can still use this equation. Because the flow rate, we need to convert the volumetric flow rate to meter cube per second. It is feet cube per minute here. So to convert 15 feet cube per minute gives us 60 seconds. So the minutes cancel out. We need to eliminate the feet cube also. 1 meter gives us 3.281 feet out. So our feet cube and feet cube cancel out. Minute cancel out. So we are left with meter cube per second. And that becomes our volumetric fluid. Yeah. Now our density is in gram per centimeter cube. So we need to convert our density also to kilogram per meter cube so that the unit become consistent. Our mass flow rate from this relation, mass flow rate by meter cube cancels the meter cube. Let me go over again. We need to find the mass flow rate in kilogram per second. We have the flow rate of water flowing to a pipe as 15 feet cube per minute. And then the density given is 1 gram per centimeter cube. First of all, I said that the density is mass over volume. You should just forget about the flow rate. If there is flow rate, then it should be attached to both of them because the flow rate is just per time. So if both have per time, it's fine. We need to convert our volume flow rate to meter cube per second because you realize that kilogram per second is actually an SI unit. And then with the SI unit, volume is measured in meter cube and then times in seconds. So we need to convert our volume flow rate to meter cube per second. So we have feet cube per minute. We need to eliminate this minutes. So 1 minute gives us 60 seconds. So this and this cancel out. So at this point, we have feet cube per 60 seconds. Now we need to convert the feet cube also to meter cube. And I said with when you have cubes and some powers, you just have to do the normal conversion after we apply the powers too. So 1 meter is 3.281 feet. You just have to cube both sides. And then our feet cube can cancel this. Please, when you are cubing both sides, it means you are going to cube what's here also. So our meter cube, our feet cube divides our feet cube here. And then we are left with 15 meter cube per 60 seconds times 3.281 cube 7.079 times 10 to the power minus 3 meter cube per second. Now that you have our volume in meter cube per second, our density here is in gram per centimeter cube. So you need to convert that into kilogram per meter cube. And then we know the conversion already. 1 gram per centimeter cube is 1000 kilogram per meter cube. So from this relation, mass flow rate is density times volumetric flow rate. So you can just multiply these two and then we will get 7.079 kilogram per second. Now yesterday Doc spoke about process unit and then we also spoke about first he spoke about unit operations and the unit processes. And then I believe that one we understand it by now. So the process unit is actually what it's like an equipment or a system where the unit operations or the unit processes takes place. So when you take something like a mixer, the mixer here becomes our process unit, which is the equipment. And then what actually goes in the mixer is mixing or let's say blending, which is a unit operation. Please do you get it? So that's the relationship between process units, unit operations, and the unit processes. So the process units are actually equipment. And also we'll also be looking at a dryer here. And with the dryer, just like the name goes, it's used for drying. So probably we'll have a wet feed entering or let's say a semi-solid which has some form of liquid in it. So it enters the dryer. What the dryer does is that it removes some water vapor from the feed and then so you realize that the output here will be two. one stream for the water vapor, which is this, and then the other stream will be for the dried product. So like when you have any wet problem, which talks about a dryer, just know that there will be one stream for water vapor, and then there will be another stream for the dried product. So this gives us two outputs. Unlike a mixer, that gives us just one output. And then distillation column. So that one operates based on the difference in volatility. So when you talk about volatility, you are just trying to see differences in their boiling point. The rate at which, let's say, a liquid converts into a vapor phase. So we have the feed entry. So just like I said, when you talk about the distillation column, one feed enters because it's a separation technique. So the feed enters and then we are going to separate it into two or more components. We have our upstream here and then our downstream. So the vapor leaves, the more volatile component leaves at the upstream, and then the less volatile leaves at the bottoms. So anytime you have a wet problem, it talks about distillation column. And then there is only two components entering the feed. So let's say the feed consists of A and B. The feed consists of A and B. When they enter the distillation column, just know that one will be at the upstream and then the other will be at the bottom stream. Yes. So there is just one feed that enters. But then distillation, we know it's a separation technique. And then we can't separate just one component. Even though it's just one feed. When you say feed, you are just trying to say an input. So just one input entering. But then with that feed, it contains or it might contain more than two components present. So the feed engine, let's say it could be a mixture of A and B. And that mixture A and B is what we call the feed. So just take this as something like a pipeline which consists of two components A and B. Right? So just one feed, it enters the distillation column. And then the distillation column is going to separate these components by means of their boiling point. So the more volatile leaves as the upstream or as a vapor, and then the less volatile leaves as a bottom. Reactors. So reactors, it houses a reaction. I think the reactors will somehow be like the mixer here. You can have more than one feed entry, and then but then with the reactor, the output could be one or more. It depends on what we are looking at. So this is an example. We have a reactor here. This is just a block diagram. We have a reactor here. We send in our fresh feed. For reactions, because we have so many reactions, we have reactions that require just one feed, and then reactions that require more than one feed. So when it comes to reactors, it depends on what you're actually looking at, how the problem is being faced. So we have our first feed which enters the reactor. And then when it enters the reactor, there's a reaction that takes place. And you can get more than one output, like I said, for reactors. And sometimes if you want to do a recycle, so recycle means probably wanted to convert some amount of the feed into the product, but then some of the feed were not converted. So you recycle them back into the reactor. Right? And then when you are recycling it, you can't just add because this what we are doing here is we are just looking at a company, right? Like a whole system on its own. Let's say you visited Ghana Gas or a certain company, right? They are not just lines, they are actually pipelines. So you can't say you are just going to add a recycle just to the other feed. You need another unit, which will be a mixer. So here, this is a mixer. You put in or you connect your recycle and then your fresh feed, they mix and then you send it back into the reactor. So the actual problem will be that we are going to combine everything that you've learned from here and then you are going to draw a whole flow sheet on its own. Right? Because with this reactor alone, realize that we have a reactor and then we have a mixer at the same time. You could get a problem that after the reactor, the output that you are getting, you want to separate them. So you need another distillation column. We have a reactor here, and let's assume you are trying to crack a long chain hydrocarbon, right? So let's say you are cracking heptane. Now, when the heptane enters into the reactor, we expect that all the heptane gets cracked into lighter components, let's say methane, ethylene, and let's say propylene, so that they come out. Let me take it over
Okay.
again. We are trying to crack, let's say, heptane into methane, ethylene, and then propylene. But in actual sense, not all of the heptane will be cracked. So as part of the effluent or the output from the reactor, you might get your methane, ethylene, propylene, and then you still get some amount of the heptane coming out because it wasn't cracked. Not all of them were cracked. You get it? So you try to separate that heptane and then you send it back into the reactor. But then the reactor just have only one feed inlet. It just have only one feed inlet. So how are you going to send it back? You need to mix it with the fresh feed. So there is a mixer here. Now mix the two of them before it enters into the reactor again. That process is what we call the recycling. I don't know if you've been to a corn mill before, like the way they do it. Sometimes they send it back again and then they mill it.
Doesn't mean that the recycle is coming from the reactor. So I was just pointing out to the person that sometimes with the recycle, it can be coming out from the reactor, but then it's also possible that you are recycling from another unit that comes after the reactor. So maybe after this
Yes.
reactor, there were some other units, and then from those units, you wanted to send back some of your material and feed it again into the reactor. So recycle just means that you're taking something that is further down in your process and sending it back to a unit that was before it in the process.
So just take it like this. After the effluent here, probably we had the heptane and then let's say methane here coming out as one from this, right? We need to recycle the heptane, but then the heptane is mixed with the methane. So we need to send it to another unit that will separate the heptane from the methane, and then we can now recycle the heptane. So sometimes it's not always like you will get the recycle straight from the reactor. It's not even feasible because what will come out, I'm not too sure that you can get the reactor giving you different output that separate everything already. Unless maybe you have a separating unit inside the reactor that will separate it before it comes out from the reactor. So that one you can just do the recycle. And then in most cases, what will come out from the reactor will have both your desired product and your undesired product. So that you can separate it and then you do your recycle. So the last thing we'll be looking at is the evaporator. Now the evaporator operates just like the dryer, but then the evaporator doesn't dry the thing completely. It just tries to get a concentrated amount or a concentrated solution of what you want, or you try to desire or get a certain concentration that you want. So let's say you have a mixture of salt and let's say water, but then you want to get a concentration or a solution where there is so much salt in the mixture or the solution that you have, right? So you try to evaporate some of the water and then you are left with a lot of the salt in a small amount of the water. But then with the dryer, you are trying to dry the thing completely. That is the main difference between the dryer and the evaporator. So with the evaporator, you need two inlets because the evaporator itself needs a steam, something, as a source of heat to help with evaporation. And this one we are looking at here is a multi-effect. So this alone is an evaporator. But then because you are looking at a multi-effect, like you're having multiples of the evaporator in series, you are connecting them. So the feed enters, right? And then the steam also enters. It heats up the feed and then some amount of the liquid present evaporates. Right? And then we get our liquid, or let's say our feed, which has now be a bit concentrated. We pump it again to the next evaporator. Now the one that comes out here is the amount of water that has been removed from it. I'm talking about this portion. This this one that comes out here is the amount of water that has been removed. Right? And then this one that goes here is our steam. It's a multiple effects evaporator. So the same steam flows into the next evaporator. Here we need a pump because the feed they are always in a liquid state. So you have to pump it. And then because this one the steam is a gas, it can flow. Right? Then it moves to the next evaporator. It enters the next evaporator. The steam further heats it again, and then it removes the amount of liquid, and now the feed now becomes a little bit more concentrated again. We pump it into the next evaporator and then the process goes on. So it goes on till we get the concentrated product that we want. So if let's say you want to increase the concentration of the salt in the water to let's say 90, but then initially it was 20 with 80% of water, then we can do this till you get to that 90% of salt that you want. And you also have an absorber. So when you say absorber, it's just an equipment which is used for absorption or stripping. Another name from the absorber is the stripper. And what is that? It does is that the absorber is used to strip or let's say remove one component from a mixture. Right? So we can have, let me use a diagram to explain. So we have a gas which is entering. Right? The gas here is a feed. It consists of carbon dioxide and then methane. And then it enters the absorption column or let's say an absorber. Now the whole idea of the absorption is that you are trying to put in another component which has a high affinity for one of the components here. Right? So the one enters the absorber. The three is an absorbent. That absorbent here has affinity for one of these gases. So let's see, in this case, it was the CO2 that had the affinity for. So it can actually dissolve the CO2. Now when it dissolves the CO2, now the CO2 and then the lean absorbent here become one mixture. And then the methane also becomes another mixture. So it's like they become two mixtures. And because the lean absorbers, you know how gases flow. It enters and then it flows up. So as it's moving up, the lean absorber flows from the top to the bottom. So this is like a sprinkler. That's whilst the CO2 and then the methane are rising up, the absorbent will just be dissolving the CO2. And then because this is a liquid, they drop pressure, they drop by gravity. So here they drop by gravity, CH4 going up because it's still a gas. But then the carbon dioxide dissolves in this absorbent. And then because the absorbent is in the liquid phase, it dissolves with the carbon dioxide and then they come out. So what you lean and then which is when you say lean, it's like it's it's pure, something like that, like a pure one. Yes. So a pure absorbent. And then the rich here means that it's absorbent. So now this one consists of absorbent and then the CO2. So the absorption, I was saying that the whole idea, absorption is like a separation technique. We have a feed, or let's say a dirty gas, which consists of both CO2 and then methane. Now, the whole idea is to separate the methane from the carbon dioxide. That's what you are trying to do. And then we want to use an absorption process to do that. And then with the absorption, so the absorption is our unit operation. And then our absorber here becomes our process unit. So we feed the dirty gas into the absorber. And then the way of absorption, we have to feed in another liquid or another substance that can actually dissolve one of the components we have here, right? And that component that comes in fresh is called a lean absorbent. So when you say an absorbent is a substance that dissolves another substance, something like that. So our lean absorbent here, whilst our gases, you know how gases move, whilst the gases rises up the absorber, the lean absorbent, there's a sprinkler here that sprinkles the lean absorbent. So as the gases are rising up, the sprinkler sprinkles on the dirty gases. And then for this particular case, the lean absorbent has affinity for the carbon dioxide. So it dissolves the carbon dioxide and then both the lean absorbent and the carbon dioxide comes out, right? So the carbon dioxide dissolves in the lean absorbent. Now when it gets dissolved in the lean absorbent, it comes out as absorbent plus carbon dioxide. And that's why we call them rate absorbents. It's rich because it's now not pure. It has carbon dioxide attached to it. And then here it's lean because it's very pure here, or let's say it's clean. So it absorbs the carbon dioxide and then you are left with just methane. That's the whole idea of absorption.
Liquid carryover in the unit. Let's say liquid carryover of the absorbent in the clean gas. How can we avoid that?
So there's something they call a DN trainer or demister.
Yeah.
So some solid thing that is there, which kind of knocks the. So usually the absorbers have something at the top where the gas is living, they call it the de-entrainer or the mist eliminator. There's some solid bar which the gas is able to move around it, but the liquid kind of hits it and come back.
Does it mean that the CO2 would make it impure?
Yes, yes. So now the CO2 is an impure, is an impurity to the absorbent. And then the absorbent is also an impurity to the CO2. When it's an impurity, just like a foreign material, the flash separator. So it's also a separation unit or separation process. We have our feed, but then the feed consists of a liquid and then a gas. So you just have to separate the two of them. And we separate them by means of pressure drop. So you just drop the pressure and then the gas escapes from the liquid. Then you get your two outlet. The whole idea of this is to know the amount of input you need and then the amount of output you also need. So anytime you are working with a flash separator, you should know that there will be two outlets, a vapor phase and then the liquid phase. Okay, sure. So that will be all for the first lecture. I know if I can continue with lecture 2. Okay. So this part scientific notation. I think this one you've already done it in your engineering mathematics or all that. Please continue or
Francis,
end it here and then continue this some other time.
yeah, I think it'd be best to start the
Yeah,
lecture
hello.
2 tomorrow because they've met a lot of new things today. But someone is asking that we go over the last one.
The last one.
I think that's the
Okay.
flash separator.
Yeah. Yes. So the flash separator, I'm saying that the feed consists of a liquid phase and then a vapor phase, right? But then they are mixed, just like a mixture. So it enters the flash separator and then the flash separator operates by dropping the pressure of that feed. So when it drops the pressure, the feed just leaves. Just like if you have a coke, like you shaking it and then just opening it once. You see how the gases tend to leave the liquid phase. That's how the flash separator works. So you drop the pressure and then the vapor leaves the liquid phase. So you get the vapor moving up and the liquid coming down. Yes, so they do it yourself here. Try the A, B, and C, and then you can compare your answers.
For the flash on the flash separator.
Uh-huh.
So for that one, it doesn't necessarily have to be separating it from a residue, but both cases, the vapor and the liquid can be a product that want to be achieved.
Sometimes, when it comes to separation, it's a whole lot. It involves what you want, right? Sometimes both the vapor and then the liquid phase, you like them, you need them in the plant. So let's say maybe you are doing some form of hydrogenation. Okay, you want to hydrogenate, let's say, an alkene compound. You will send your alkene and then your hydrogen into the reactor, and then the hydrogenation takes place. And when it takes place, what comes out, maybe some of the alkene wasn't converted. So let's say you try to separate the alkene um from the ones that have been converted. Like let's say you try to separate the alkene from the alkene because you've hydrogenated it. Now when you separate them here, so let's see, you try to separate them here. You have your alkene and then let's say alkene. And then it's possible you can separate them using a flash separator. When you separate them, you can get, let's say, your alkene here and then your alkene here, right? Your alkene, you need it for another process. And then your alkene too, you can feed it back to go and do the hydrogenation again.
Uh,
So you try your assignment and then you compare your answers. You will continue tomorrow.